All right, welcome to Lab 7. This week, we're going to talk about collision resolution methods with hash maps. So a few announcements. Midterm grades are back. If you need a request, do that. However, it'll take a while for that to go through. We wait until the deadline for that before we process those requests. Project 3 is out. It's due the 16th. Then you have some labs, handwrittens, autograder quizzes to do. Make sure you do those. Today, we're going to talk about hash maps and hashing functions, and really why we need collision resolution, as well as ways to resolve collisions, and then performance, dynamic hashing, handwritten problem, and all that fun stuff. Okay, so before we go into that, let's talk about Lab 6 handwritten solution. And just to refresh, this was you're trying to find symmetric pairs. So for this solution, what you had to do, the quickest way to find unique pairs is n squared. So you do that double for loop to find those unique pairs. Whoops, let's change that to black. And then inside that for loop, you figure out the sum of that pair that you're currently looking at. And you say, hey, actually, let's step back a little bit. You're going to keep an unordered map where the key is the sum and the value is the pair of that sum. So now that you're iterating through and you're finding every single pair, you take the sum of that pair and you say, hey, in my map, do I already have this sum? If so, that means I have a symmetric pair and I can look at the value of that key, the sum. If not, then let's put this one in. And you can see that here, we take the sum. Then we check to see if that sum is already in our map. If it is in our map, then we see out the value as well as our current value for both those pairs. If it's not in the map, we put it in the map, taking the sum of our current pair and inserting the pair as the value of that key. Any questions on this handwritten problem? I believe you could do this with brute force, not using a hash map and n cubed, but using the hash map, you're able to get it down to n squared in open memory. Good thing to point out is when we're figuring out to see if there's already a sum in the map for our given pair that we're looking at, we use .find rather than the square brackets, just so that we don't create a new element if one doesn't already exist. If you like code golfing, like me, and you like elegant solutions, instead of using .find, you could use .count. And what .count does is it doesn't return an iterator. It either returns 0 or 1. 1 being the key is in the map, 0 being it's not. So here, rather than keeping track of an iterator and doing iterator.end, we just do .count. And really, honestly, you don't even need the equals 0. You could honestly say, if not .count sum, then you make it. Else, you know that a key exists, and you can use that key, the value of that key, rather. Any questions for this solution? All right, cool. Let's continue. So hash functions. So up until today, we know all about hash maps and using them. And now we're going to talk about the implementation of them. So what is a hash table? Well, you implement these abstract data types. And the average case is O of 1 for lookup, delete, insert. And what it actually does under the hood is it keeps track of this vector. And you have this hash function, as well as taking the modulo, the size of the vector, and it tells you where to look in the vector for that key. So you give me a key, I have this hash function that says the index to look in this vector. And that's essentially a hash map under the hood. In a perfect world, every key maps to a unique index, but that's not always the case, and we have collisions. So let's talk about how we resolve those collisions. But first, it's worth noting that you always need to use the modulo operator as well. Our hash function just gives us an index. It doesn't guarantee that that index is within the size of the vector. So after you take your hash function to get an index, then you have to take modulo, the number of buckets or the size of the vector, so that you can guarantee that that index that the hash function returned fits within the vector that you have allocated under the hood. And that's essentially how you get your index. You take this hash of a key, and then you modulo it by the size of the unordered map, or the size of the vector. Any questions on that? Cool. Okay. Hash function invariance. So what our hash function needs to guarantee is that first, it's consistent, that every time we have the same key, it returns to us the same index. If it wasn't consistent, that would totally defeat the purpose of a hash map, because how can we find if that value for a key exists if we don't get the same index for that key every time? The second thing we want our hash function to do is be efficient. The whole purpose of using this hash map is because we want to guarantee, that O of 1 lookup, find, delete. And we're going to need an efficient hash function. If it's not efficient, that'll bottleneck our process, and it might not be O of 1 anymore. So those are the two invariants that we want: consistency and efficiency. Let's look at some hash function examples. So here we have 3 examples of hash functions. And I want you guys to look at this and tell me which invariant these ones all break. Or maybe not which invariant they break, but what's the issue with these hash functions? All these hash functions take in a string and they return to you a hash index. Anyone want to take a stab at it? What's wrong with these hash functions?
I think the left 2 are problems with consistency, and the right one is there's a loop, so it's a problem with efficiency.
Yeah, kind of, for sure. You said the left 2 are problems with consistency. They're actually all kind of problems in that they all create a ton of collisions. So you could argue that they're all kind of problems of efficiency in the fact that there's a lot of collisions that these cause. For example, with hash 1 and 2, if you take in a string and you always return 1, no matter what the key is, you're returning the same index. So you're going to guarantee to get a collision every single time. And remember, collisions are bad. We don't want collisions. And this is kind of a trick question because we didn't talk about collisions yet, but collisions are bad. We want to avoid those. If you look at hash 2, what hash 2 does is it just looks at the first character of the string. And it says, I'm going to hash based off that first character. Well, AB and ABCD, those 2 strings would have a collision. And really, any string that has the first identical letter would have a collision. And this third one's kind of tricky, but you can also see if you dissect it a little bit that there'd be tons of collisions too. So all of these kind of have a problem with efficiency because they have tons of collisions. Okay, so now let's run through one of these hashes and index it ourselves. So given 3 keys here, what does the hash function return for these 3 keys? Our hash function being the 1 right there. Let's change our color too. So I'll give you guys a second to figure out what these 3 keys, the hash that these 3 keys would produce. And then feel free to, put it in chat or voice your opinion. And one more thing to note, our hash function we're just asking for what this returns. Don't worry about the size of the container yet. Perfect, we have an answer. So 25, 3, and 5, yep. Because all this hash function is doing is it's just figuring out the first letter and doing some ASCII arithmetic based off of that. So, Z minus A would give you 25, whereas A minus A would give you 0, and all the other numbers fall between that. So, yep, this is what the hash function returns for these 3 keys. Now the question is, what about the buckets? So now we have to consider our modulo, the size of the vector, to see which buckets these 3 keys would lie in. And remember, the 3 keys were 25, 3, and 5. Okay, we have an answer, 5, 3, 5. Yep, and the way that we get this is our final index. The buckets that it would fall under is the hash modulo the size of the container. And here, the size of the container is 10. So we take all these values, mod 10, and we would get 5, 3, 5. Notice with this, we would have a collision from zebra and fest. Okay, so let's talk about how to resolve those collisions. But before that, any questions on how we figured this out? First, the hash key, and then second, the buckets that those hash keys would be at. This camera keeps on autofocusing. Cool. All right, let's continue. So collision resolution. In lecture, we gone over 2 ways to resolve these collisions: separate chaining and open addressing. And really the difference between these 2 is separate chaining handles collisions by using a linked list, whereas open addressing just throws it at a new location. And we talk about different methods of open addressing and where that new location would be. But, if we look at this example, Sandra and John have a collision. They both map to the same bucket. So with separate chaining, what do? Well, when we map Sandra and we already see that John's there, we just make a linked list and put Sandra after John at the same bucket. Whereas with open addressing, John and Sandra both have a collision. And what we do is, rather than use a linked list, we just do, looks like in this case, linear probing, and we throw Sandra right under John for the bucket. And that's the difference here. So let's talk about separate chaining. Upon collision, the new element is just added to the back of the bucket's linked list. Each of these buckets have their own linked list, and a collision just adds to the back of it. So that being said, what would be the best case, the average case, and the worst case of lookup and insertion into a hash map that uses separate chaining? Anyone have any idea? The best case, average, and worst case of looking up using separate chaining? Well, the best case would be there's no collision. So in this linked list, when you index into the key, your value is at the first location. What would be that? Yep, exactly. So the best case would be O of 1, and that's when there's no collision. When the linked list that you're looking up, size of 1. Average case is a little trickier. Let's do worst case next. The worst case would be what? Well, you are looking up a bucket and every single key that every single key value pair in this hash map is in that bucket. So this giant linked list. And the key value pair you're looking for happens to be the last one in the linked list. Then that would be O of what? O of n, right? Because n being the number of key value pairs in the linked list, or rather the hash map, if they're all thrown into one bucket, there's going to be O of n values there, and you have to go to the very back. And the only way to get to the back, well, you have to look through every element, and it happens to be the back, so that takes O of n time. Average case, well, you can kind of assume that if we have, the average case would be, well, distributed perfectly. So you could say number of key value pairs over number of buckets. And I think it would be +1. I think it would be O of this. O of 1, because you have to index into that current bucket. And then how many elements are in that current bucket? Well, assuming that all the key value pairs in this hash map are distributed perfectly, it would be, well, the number of key value pairs over the size of the map, the underlying vector. And then this would be, well, we say O of 1 here because the number of key value pairs is typically, it's kind of confusing. We'll talk about it later, but since the load factor is never going to go over 1, number of key value pairs is always going to be less than the number of buckets. So this would be less than 1. So it'd be like O of 2, which is still O of 1. Kind of confusing right now, but we'll talk about load factor in a second. Okay, so that is separate chaining, which is one of the ways to resolve collisions in a hash map. Now let's talk about the other way, open addressing. And with open addressing, there's really 3 different methods that we're going to explore. The first one being linear probing. And the way that we do linear probing is we let k be the key and h of k be the hashed value that we get returned from the hash function. Then really, our index that we're going to get, that we're going to produce, equals that hash key plus I mod n. So really, this looks exactly the same as what we just talked about, but the only difference is this I. And what this I says is, if there is a collision at that hash key, start at 0. If there's a collision, then try 1, then try 2, then try 3, ... until you no longer have a collision. So what's that look like? Well, let's check it out. So let's do an exercise with, this is our equation for linear probing. And once again, our hash key that the hash function returns plus I, starting at 0 and incrementing until there's no longer a collision. Anyway, so if we insert these 4 items, where do the keys end up? So let's first just say what the hash function returns. So what does the hash function return for cat? What's going to be our h of k? Let's figure out our h of k for all 4 of these values first. And we're going to use hash 2 over here. Perfect. Cat would give us a hash function of 2. Cop would be the same because what we're doing here is just looking at the first letter. Ear would be 4, and then this would also be 2. So this is our h of k for these 4 keys. Now let's throw them on our map. So remember, I starts at 0, and we only increment I when we have a collision. So with cat 2, we check in our vector. Right now, our vector is below, and we say it's a size of 6. Okay, so with cat, it's index of 2, a hashed index of 2. So we check, is 2 empty? It is perfect. I of 0 works perfect for cat. Okay, now we try cop. and we say, okay, cop wants to map at index 2, and there's a collision. So the next thing we do is say, well, I of 0 didn't work, so let's try I of 1. So remember, h of k is, in this case, 2 plus I of 1 gives us 1 mod n, which is 6. So that would be 3 mod 6, that's still 3. And let's check that. 3 is open, perfect. Okay, ear. So ear starts at 4, and I would be 0, so it'd just be 4 mod 6. And there's nothing there, so we just lay there. And now we have cardiographer, which maps to 2. There's a collision there. So let's try I of 1, maps to 3. There's a collision there. I of 2, collision. I of 3, no collision. And that's our answer. Now, what if we added duck to our hash map? Where would that go? And that's a question for you guys.
Wouldn't it go into 0 because it should go in 3, but then you'd increment I 3 times, and then taking the modulo of that would be 0.
Exactly. So the first thing we do is get our h of k. You said that that should go at index 3. We check index 3, and that's full. So we keep on incrementing I, and it wraps around because modulo, once we get to a value of 5, it wraps around to 0. And when it wraps around to 0, that's open. So we put duck at index 0. Perfect. Any questions on that? All right. So that's linear probing. Pretty straightforward. This week in lab, as your lab exercise on the autograder, you're going to have to implement a hash map using linear probing. It's a pretty difficult lab and hard to debug, so start early. Okay, the next open addressing we're going to talk about is quadratic probing. Pretty similar to linear probing. The only difference is rather than just doing plus I, we're doing plus I squared. And remember, I still starts at 0. Okay. So let's do this. Using the 4 examples that we had last time, those all hashed to 2242. And now let's throw them into the table. So let's take cat, and we say, okay, cat has an HOK of 2. And we're going to have 0 be our initial I. 0 squared is still 0. So we're going to check to see index 2, if that's open. It is. Perfect. We're going to throw cat there. Cop. We're going to check. H of k is 2. I is 0. Mod, in this case 10, because the size is now 10, is 2 open, and it's not. So we're going to resolve this collision now by taking an I of 1. So in this case, if I is 1, it would be 2 plus 1 squared mod 10. And that's going to give us 3. And we're going to see if that's open, and it is. Okay, now we have ear. H of k is 4. I is initially 0. We're going to see if 4 is open, and it is. Good there. Now cardiographer. Oops. H of k is 2. We're going to see if 2 is open. It's not. So now we're going to take an I of 1. And 2 plus 1 gives us 3. That's not open either. So now we're going to take an I of 2. And if h of k is 2 plus I of 2, that's going to be 2 squared mod 10. And that's going to give us 6. And 6 is open. Okay. And now, once again, question for you guys, where's duck going to go? Remember, the hash of duck is 3. Okay, we have an answer for 7. That's correct. So the first thing we do is we say, okay, we're going to check index 3 because that is our h of k and I is initially 0. That's taken up. increment I to 1, and we're going to check 1 squared is still 1. So 3 plus 1 is 4. We're going to check 4, taken up. Now we're going to do I of 2. 2 squared is 4. 4 plus 3, h of k, gives us 7, and 7 is open. So we're going to throw duck there. And that's quadratic probing. This is nice. When you have, I guess the benefit of this over linear probing, one of the benefits of this is you don't get this cluster of keys as much as you do with linear probing. Because if you have a lot of keys that map to the same area, given the hash function, those are going to start clustering, and it's going to start, really declining your performance. Whereas linear probing with, or rather quadratic probing, when you have collisions, it spreads the keys out further than linear probing does. And it does that, exponentially, or I guess squared. Okay, cool. So the final open addressing method is double hashing. So this one looks a little confusing, and you use 2 hashes. So our first hash is h of k, same as before. Our second hash is now f of k. Still have an I that starts at 0 and increments upward. But now what the case happens is when we have collisions, we multiply I by the result from the hash of f of k. Besides that, it's the same as before. So and then obviously we still mod the size of the hash table. So let's look at an example. Using the 4 keys that we used before, cat, cop, ear, and cardiographer. Now we have 2 hashes because we're doing, that shouldn't say quadratic, that should say double hashing. Now we have 2 hashes because we're doing double hashing, and those are provided below. We give you those. And now let's figure out where everything goes. So with cat, we initially look, and our h of k is 2 and our I is 0. So we're initially going to look at 2 plus 0 times 19 because f of k is 19. So we're just going to look at index 2. That's open, so we can throw cat at 2. Now with cop, once again, we try 2 plus 0 times, in this case, 15. That's going to have a collision. So the second thing we try is going to be 2 plus 1 times 15, which is our f of k. And then we're going to mod that by 10. And that's going to give us 7. Because it's going to be 17 mod. It's going to be 17 mod 10. Okay. And now ear hash is at 4. So I is going to be initially 0 and 4 is open. So we can just throw that there. I keep on getting this. Okay, well, throw ear there. And then cardiographer is going to be a little more confusing. We're first going to try 2 because that's our h of k. That's taken up. So then we're going to say I is 1, and we're going to have 2 plus 17 mod 10. And actually, we're good. That gives us 19, and we can throw it over here because that's open. And that's what our underlying vector would look like using double hashing. Any questions on double hashing?
Yeah, isn't there an issue?
Yeah, go on.
What do you do when hash 2 is like the size of the number of buckets? So like if it hits the wrong thing and then you try to take the modulo by adding I times hash 2, like it would just hit the same place every time, right?
Yeah. So that would be problematic. So you'd have to avoid that. One way to avoid that, I believe, would be to use the size of the bucket being a prime number. But that's a good point. Common exam question, multiple choice. We give you all these keys and we say, okay, what's our vector going to look like after you insert all these keys in? Using, X, where X is either quadratic probing, linear probing, double hashing. And you'll see a lot of examples of that in the practice questions when you prepare for the final. Okay, and that was a good point. What happens when our hash of 2 is a multiple of the size of the container? And that's very problematic because you'll just get repeats forever. So you have to avoid that with double hashing. Okay, so now let's talk about deleting elements, because hash tables not only insert, but we should be able to delete elements from those too. So how are we going to cover that? So assume that we inserted cat into bucket 2, and then we inserted cop. Cop should have been at bucket 2, but we threw it at bucket 3 because there was a collision and it would appear that we're doing linear probing. Now we're going to try to remove cop. Or no. Now we're going to try to find cop after removing cat. So, we want to remove cat. So we hash cat to see if it's in our map. Then we look at the index it gives us. It gives us index 2. And we say, oh, perfect. Cat's at index 2. Get rid of that. And now we have an issue, because if we want to find cop, we say, well, cop should be at index 2. So we look at index 2 and there's nothing there. So in that case, we might stop looking and say, oh, we're trying to remove an element that doesn't exist, or we're trying to find an element that doesn't exist. So it's clearly not in our hash map. So when we remove values from a hash map, we almost have to say, at least with open addressing, we almost have to say like, hey, this value was deleted. Keep on looking. So if we did that, after removing cat from our container, and rather than just making it look clear and nothing's there, if we say some type of way that this element was deleted, then when we try to look up cop, we first look here and we say, cop's not here, but this element was deleted. And since we're doing linear probing, I'm going to check the next element just in case. Bam, checked it. It's cop. We found it. Any questions on that? And once again, if you didn't do this, then you might say an element doesn't exist when it really does further down the chain after a collision, after you had some collisions. So let's go through an example of this. And keep in mind, when you're doing the lab, the autograder portion, that you're going to have to keep track of deleted elements. And you're going to have to treat them kind of interestingly. So we have these key value pairs inside our vector. And the first thing we want to do is erase cat. So we hash cat. That gives us an index 2 using this hash function, 2 mod 10 still 2. And we look at 2. And we say, oh, perfect. Cat's actually there. So let's delete it. But not only do we delete it, but we say that we deleted it using this kind of notation. Now we want to erase cardiographer. And cardiographer maps to 2. So we're first going to see if it exists. And we check 2 and we say, well, it's not here, but this element was deleted. So since we're doing linear probing, check the next one. And the next one's cop. But we still can't conclude that cardiographer's not here because, there could have been a collision with cop. So really, when we're trying to erase cardiographer, or at least find it, we have to keep on looking until we get an empty cell that was never deleted, or we find it. So we see cop. Cop's not cardiographer, but it's not empty. So we keep on going. Get ear, not empty. Keep on going. Cool, we found it, cardiographer. And now we want to erase that. So we throw deleted here to erase it. And now we want to insert cardiographer into our hash map. So we hash that, and that gives an index of 2. So we want to throw it right here. And we can't throw it there because there's nothing there right now. It's just a deleted element. But, before we throw it there, we have to make sure that it doesn't already exist in the map. So in this operation, we first have to check, since there is a deleted here, cardiographer could exist further down the chain, and we won't want to insert it twice. So we can check, 2 is deleted, so we keep on looking. 3 is not deleted, but it's not empty. So we keep on looking, and we keep on going until we find an empty cell when we want to insert cardiographer. And we get to 6 and we say, oh, this is empty and it was never deleted. So we know if cardiographer was in this hash map using linear probing, it would have to have been seen already. But it's not. So now that we reached this empty cell, we go back to the initial place we wanted to insert it. And we say, all right, we're going to throw cardiographer right here. Any questions on that? This is a very common bug when you're implementing the hash map in the lab. And just remember that to simplify it, when you're looking to erase an element or insert an element, you have to keep on checking for that element until you find an empty cell, a cell that was never deleted. Then you can conclude that that element, is not in the table or whatnot. And then you can throw it back in the table in the original position that you hashed out. Okay, cool. Let's continue. Let's talk about performance and load factor. So with linear probing, when we inserted like cat, cop, ear, cardiographer, we obtained these collisions. Cop had a collision, cardiographer had a collision. And this kind of just shows that the more collisions you have, the worse your performance gets. And we want hash maps to be O of 1. But as you start piling up these collisions, it might become closer to O of n. So let's talk about load factor, a way to evaluate performance of a hash map. So load factor, to put simply, is just the number of elements in the hash map divided by the number of buckets. And the higher the load factor you have, the more elements you have than positions for those elements to be, the more likely that you have a collision and the more likely your performance is degraded. So how do we increase the performance and reduce the number of collisions? Well, there's a few ways to do that. Use good hash functions that avoid collisions. When we mentioned the hash function that always returns 1, that would be like a terrible hash function. Keep your load factor low. As long as the load factor, as long as there's less elements, the number of buckets, typically below 3 to 4, your performance is all right. So going back to talking about linear probing and what the complexity of linear probing is in the average case, we said it was O of 1. We said it was O of 1 because we assumed that the load factor was less than 1. So we assumed that the number of elements was less than the number of buckets, which would give us an O of 1 complexity in the average case. And then also the third point of increasing performance or reducing collisions is to use prime numbers for the table sizes. And that's just because when you're modding by a prime number, less likely of a chance that you'd get a collision. And then that'll also resolve the point that a student brought up earlier in lab with a double hashing. Any questions on load factor and performance? It's also worth noting that linear probing does much better with having a higher load factor than open addressing does. Because open addressing just throws it at the next open place in the hash map. I think in lecture, you go over a table that looks at how degraded the performance gets with increased load factor. And as you get above 0.5, I think it is, your performance gets destroyed in open addressing. Okay, so now let's talk about complexities. Where K is the number of keys and N is the table size. The complexity for searching, inserting, or deleting is going to be 1 plus K divided by N in your average case. And it's going to be O of K in your worst case. And that's just because the likelihood of collision is K divided by N. And this O of 1 just comes from looking at the first position. Then O of K worst is if, in linear and with a linked list, if all the elements map to the same bucket, or an open addressing if there was a giant cluster of all the elements and you had to resolve the collision by going through all of the elements to find an open position. Space complexity, it's O of n average and O of n worst. Assuming that we keep a good load factor where K is less than n, and we're not too crazy about the load factor, then it's going to be O of n. Any questions about the time or space complexity for hash tables? Cool. Just to summarize, some comparisons between separate chaining and open addressing. Remember, separate chaining is linked lists. Open addressing is the three other ones that we talked about. With linear probing, quadratic probing, double hashing. Few things to note is separate chaining uses extra memory because linked lists use memory. It uses dynamic memory because linked lists. Handles collisions better. Can have a load factor greater than 1. That's a good thing to think about. Why can't open addressing have a load factor greater than 1? A few other things. STL implements using separate chaining under the hood. And then open addressing is simpler. Yeah. Overall, it looks like separate chaining is preferred over open addressing, but it's just more complicated to implement and uses a little bit more memory. Okay, so we talked about hash maps and we talked about, hash maps are this data structure that I give you a key value pair. And then in the future, if I look up that key, I'll get my value. And let's talk about perfect hashing. And perfect hashing is the idea that every time you throw a key in there, you know that you're not going to have a collision. That's ideal, perfect hashing. Never having collisions, O of 1. But you can't always do that. And that's why we use hash maps. Another thing to note is that perfect hashing, if you can guarantee perfect hashing, you might not even need a hash map. You might just be able to use a vector yourself. And an example of that is maybe the written, anagrams written, when we said that all the letters had to be lowercase alphabetical letters, then you could just make a vector of size 26 and you could index into it perfectly and you would never have a collision. A would always map to 0, Z would always map to 25. So I guess what I'm trying to get at here is if you can avoid using hash maps, if you can think of a hash function that is perfect hashing, you could probably use a vector and avoid hash maps. Okay, let's talk about resizing and rehashing. So when you're inserting into a hash map, you take a mod the size of the vector. If you have more elements than the size of the vector, that's problematic. So of course, as we constantly insert more elements into this hash map, we're going to have to increase its size to avoid collisions. So how do we do that? Or why do we do that first? Well, that reduces the load factor. And if we can reduce the load factor, that increases performance. Now, how do we do that? Well, we make a new container, and then we go through our old container, and we rehash every element into our new container, and then we delete the old container. Pretty straightforward. You're going to get practice with that. But let's look at that. Yeah, okay, let's look at that. So here we have our old container. We have 2 elements in it, and we want to rehash it to a new container. This old container is the size of 4. And what we do is, and we'll do this in the lab as well, or the autograder as well, but what we're going to do is we're going to double the size of the old container. So our old container size of 4, we're going to allocate a new one, that size of 8 right here. And now that we allocated this new container, we're going to go through every element, iterate through the entire old container. And if there's an element there, we're going to rehash it into our new container. And then we're going to get rid of the old container. So we first look at 0. Nothing's at 0. So we can avoid that. Now we go to 1, index 1, and we have a key, or rather a value of B. And what the 17 is saying is that the hashed index, we have this hash function somewhere, h of k, and we're saying that the hash index for B equals 17. So we're going to rehash this value inside our new vector. So in the old vector, it was 17 mod 3. Now we're going to do 17 mod 8. And that's going to give us 1. So we're going to transfer over the element to our new vector at index 1. Okay. And now we get to our next index, and that's deleted. We don't care about deleted elements. We can skip it. Now we get to 39. We do the same thing. 39 is what the hash function returns for Q. So 39, it returns 39 mod 8 is going to give us 7. So we can throw Q into our new vector at index 7. And now we remove and delete our old vector, and we're good to go. In the autograder, make sure when you create a new container, you rehash. We give you this function, hasher. Make sure you throw all of your keys into hasher when you reallocate to the new container. And then remember, you're not going to take mod of the old container. You're going to take mod of the new container. Common bug that students have. Any questions on transferring elements from a small vector to a larger one when you resize and grow the hash map? Just going off load factor, you could argue that this old vector has a load factor of 0.5 or 0.75, depending on how you look at it and how you consider what load factor is, whether or not you include deleted elements. And this new one has a load factor of just 2 out of 8, which is much better. Okay. So just a summary of hash tables. You get good time complexity. O of 1, average case. And it's great when you know the data ahead of time. Some cons of hash tables is that if you have a bad hashing function, lookups can be slow. It uses a lot of memory, and it's unsorted. Remember that. When you're iterating through these hash maps, there's no guarantee of how the elements are related to each other. I wanted to re-record this portion of the lab. In lab, I actually solved a more difficult problem. So I apologize to the students that were there. It was pretty confusing, but let's go through this. So you can expect to see a problem like this, similar difficulty at least, on the final. So I think this is a great practice problem to go over. So suppose you're given a set of n distinct words, all the same length, which is n, and we want to find a single pair of words that are similar. The definition of similar means that you can obtain one word from the other by just changing one letter. So we could go from cart to cast because we can change that letter R to a S. So they're similar. And cast and cost are also similar because we can change an A to an O and get the same word. But, cart and cost are not similar because you have to change 2 letters, not just 1. So the question is, how do we solve this problem? And in these types of problems, I like to think of the brute force solution first. So let's say that, we're given a set of n distinct words. So we could just go through every word. Let's say that we have the word cart. And we can make every possible modification to the first letter and then see if that word is in the set. If it is, we return our pair. We can make every possible modification to the second letter, see if that's in our set. If so, return the pair and do that. But that's going to be pretty slow. I mean, we're going to have to, what are all possible modifications for each letter? 26 if it's lowercase, maybe 52 if it's uppercase as well. So, and that's just for a letter, every letter it's going to be like 52 times M. And then we have to iterate through the set and see if that exists in the set. So the brute force solution is not ideal. So how can we speed it up? Well, another thing we could do is identify all the possible modifications. For cart, we can modify it in 4 different places. We could modify it in the first place, the second place, the third, or the fourth. So what if we made an unordered map of string to string, where the key was the modified version of a word and the value was the distinct word in the set. And here's kind of the crux of the problem. We don't actually need to save all possible modifications that we can make to a given word. Really, we could simplify it down to saving 4, in this case with cart, 4 different keys that all map to the distinct word cart. So when we're given cart, in our map, we could save something like this, and that would be like, okay, let's say that asterisk is changing the first letter. We could save this, and that would be like the asterisk would be like changing the second letter. Third, and finally, fourth. And for all of those keys, we can map them to cart, saying, doing this, we can get cart from by modifying that. And cart is the distinct word in our set. Now, when we visit and do this for another word in our set, let's say that we get the word cast. And when we have cast, the first thing we do is see if any of those keys, well, rather, any of the keys of cast are already in our set. So what would be the possible keys? We could put an asterisk for the first letter. We could put an asterisk for the second letter. We could put an asterisk for the third letter. And we could put an asterisk for the fourth letter. And what we could do is say, before we add those to our unordered map, see if any of those keys are already in our unordered map. If so, then we can look at the value of that key, and that will give you a similar word to our current word. Then we could just say, oh, cast. Well, cart is a similar word because we found that this was a key that was already in our map, and the value of that key is cart. So we take our current word, cast, and cart is a similar word. And that's one way that you can solve this problem. What would be the complexity of this is the next question. So we're gonna have to iterate through every word in our set. That's O of n. Then for each word of the set, we have to make how many modifications, how many keys? Well, the number of keys in this case is 4 because that's the number of letters. So how many keys are we making? We're making M keys. So we're doing M lookups, right? Because we're inserting M keys in. So this would give us O of n for the distinct words times M for the number of insertions we're doing, or lookups rather, either one. And then finally, each lookup is not O of 1. Because we're hashing through strings, every time that we hash into a string, you have to iterate through the entire string and then do an equality check. So hashing a string is actually O of n, where n is the number of letters in the string. And in this case, the number of letters in the string is M. So each hash is M. And this gives us a final complexity of nm squared. And yeah, that's that problem. I hope that was clear. Okay, now let's talk about the handwritten problem, which is slightly more simple. You're given a vector of prefixes, cat, bat, and rat. And then you're also given a vector of sentences. The cattle was rattled by the battery. And for each word in the sentence, if you can replace it with a prefix, then do so with the shortest prefix. So for example, we look at the, and we say, are there any prefixes of the in the prefix vector? There's not. But then cattle, there is a prefix. One of the prefixes is cat, and cat is contained in cattle. So we would change cattle to cat in our output vector. Rattle is another one. A prefix of rattle is rat, which is in our prefix vector. So we would change rattle to rat in our output vector. And that's the idea of the handwritten. If you want a hint, maybe you'd want to be able to look up prefixes in O of 1 time. How would you do that? And that is the hint for the handwritten problem. And that's lab. Any questions on the handwritten, or maybe the hash maps practice problem, or anything else in lab? Okay, cool. That's lab. Thanks for coming, everyone.